Good afternoon, everyone. We might have a few more people drifting into the room, but let's get started. My name is Tom Robinson. I'm the Research and Strategy Manager at the Southwest Nuclear Hub, and it gives me great pleasure to welcome you to the third in our summer series of Southwest Nuclear Hub seminars. Today, we're joined by Dr. Xin Ren from the School of Geographical Sciences. She's a postdoctoral research associate working in climate science. Take it away.
Okay. Hi, good afternoon, everyone. It's nice to meet you all. And I see there are many new faces and old faces as well. Today, I'm going to show you the work done by our group as a representative. It's about the long-term future climate prediction for UK till the next 1 million years in the context of the safety of GDF. Here. Yeah, it's an effort from the whole group, not only me. I just take it over from the group and develop it further. In the beginning, I'm going to show you the structure of the whole talk. So first of all, I'm going to give you a background. What's the problem we have and what's the challenge we need to address? And then this is the main body of my work. I need to show you the whole workflow of our work. This is the main result of our research. And then show you the result, what's the climate change in the future 1 million year in UK. And after that, I'll give you some indication of our work and our future work plan. So here's the whole structure of the whole talk. First of all, after you read my title, you might ask me, what is GDF? GDF is Geological Disposal Facility, because you can say this project is funded by Nuclear Waste Services. Nuclear waste is hazardous to human beings for a very long time, potentially beyond the next ice age. So we need to find a way to deposit and securely sell it somewhere. And GDF offers us a long-term solution to the disposal of nuclear waste. It is a network of many tunnels and vaults under the ground from around 200 meters to 1,000 meters beneath. But we can't just leave all the waste there forever and think we can hands off, because it will because it's like a long time, and we need to consider many things, including like we might lose all of our civilization. We might forget where did we bury all those waste. We might even dig holes over there and build something up there. So we need to secure the safety of the GDF for a very long time. And also, it's a waste created by our generation. We can't leave it for the future generation to deal with it. So we need the purpose of this facility is to ensure that there's no need for human intervention for the next generations. And according to International Atomic Energy Agency, containment shall be provided until the radioactive decay has significantly reduced the hazard posed by the waste. But you may ask me, how long? We can't be responsible for it forever. Then how long do we need to take care of the facility? We know that the radioactive atoms have a decay life. It's called half-life. Different radioactive atoms have different half-lives. They may span from less than 1 second to many thousands of years in the future. And in the GDF, it not only contains one atoms, but many different kinds of radioactive isotopes. So they have different half-lives. Therefore, we need to consider the longest one. In general, 1 million years is a time scale which is relevant to the post-closure safety of the GDF. So we need to consider the time of up to 1 million years. This is a very long time. And in such a long period, we can't assure the whole Earth will remain the same as it is now. Just like I'm standing here, but probably in the next 1 million years, there will be sometimes I'll be under the water, and I will even be sealed in the ice. So climate change is something will change the Earth and also the characteristic of the facility in this large time scale. Also, it will impact the integrity of the whole facility. So that's why we've been involved in this project. And we need to gain the knowledge of climate change to assure the safety of the post-closure facility, and also when we design the facility. That's why we need to predict the weather, the climate in the future. We probably don't know much about future, but we can learn from the past. Here is a curve from the recorded global ice volume from oxygen isotope for the past 1 million year. You can see here it's not keep consistent but change with time, and there are several glacial interglacial circles for the past 1 million year. So we can expect it will be will experience potentially glacial and interglacial in the future. And it is very important to the GDF because when we consider about glaciation, we need to consider many impacts, including the isostatic impacts, erosion, and many other impacts, including the very active hydrology process in the margin of glacier. So that's something very high relevant to the safety of GDF. Also, there are not only one GDF being built in the UK, but many. Some of them are inland GDF. Some of them are in the ocean. As I said, global sea level will change over the time. So sometimes those inland facility will go into the water, and some oceanic facility will go up to the air. So we need to consider the coastal process of all the facility. And also the change of sea level will affect many things, including underground water and also the distribution of salinity. So that's why this is very high relevant to the safety there. Then we know that the factor dominate the climate change in different time scale are different. For example, in our daily climate, it's a day and night cycle dominate our climate. And in a yearly climate, it's a seasonal cycle that dominates the climate change. But what causes the climate change on 1 million year time scales? Some of you might know that, some of you might not. And the first of one is the change in the Earth's orbit. You can imagine the Earth is just like a marshmallow circle around the fire, and we can decompose it into 3 parameters: eccentricity, which describes the shape of the orbit, and the obliquity describes the axial tilt of the Earth, and the precession, because the Earth is not constant, it's wobbling. So it's a precession of the X and also the precession of the orbit. These 3 parameters, they describes the orbit of the Earth around the sun. And here's an example of how the installation we've accepted at the 65° north from the sun in the future 1 million year. Yeah, we are just like a marshmallow. how you tilt your stick and how you get close to the fire can affect the height we accept, and do we accept more height over our head, or it's like evenly distributed? So this is very important. The Earth's orbit is not very challenging because we can gather from celestial equation to an even very high resolution. But the really uncertain things is the carbon emission. We know that the greenhouse effect, it will just behave like a duvet. Like the more carbon you emit, like the heavier the duvet is, and it can keep the warmth of our Earth. So we've all experienced that for the past years, and but we don't know how much carbon we are going to emit to the Earth. So we need to consider different scenarios. Here we consider the scenarios from IPCC. We might suddenly decide not to emit any carbon, but we might decide to emit all the carbon to the Earth. We don't know. So we can take many different scenarios, say what will they lead us to in the future. Then what's the really challenging things? Many of you here, we've done climate prediction or climate modeling. You might think, oh, we can just run a model. It's not very difficult. But on such a long time scale, what's the really challenging things? Can we really predict it? On 1 million year weather forecast, like in the future weather forecast, we might use some typical state-of-the-art models, just like HSM3, HGM, UKSM. We can predict the climate. It behave like a model. We give it some information about the carbon dioxide and the information about the orbit, and it will give us the climatology prediction. But even use the most like state-of-the-art server on the Earth, which is the server over here in the Bristol, it will give us 3 years of integration one day. If we do a very simple calculation, 1 million years divided by 3 years per day, divided by 365 days per year. That means if we want to do 1 million year prediction, it will take us 1,000 years. This is very unrealistic. Like our grandson, if we have, might see the result. But as I mentioned before, we need to get that information before we design the GDF, and we need to secure it in our generation. So no, we can't do that. We need to find another solution. Here's where we started to do it. Like started from more than 20 years ago, we've been involved in solving this problem. It was a project called BioClimb. And at that time, the solution we have is to use some conceptual models to predict the carbon dioxide and use some our system model of intermediate complexity to run the transient climate change. And if we want to know more information about the pattern, like the maps about the climate change, we need to run general climate models such as HAD-AM or HACM. But we can't run it for 1,000 years, so we take snapshots. We get some very key period, take the snapshot, see how it looks like. However, we want to know more, so it's a mismatch of complexity and the scale. We want to develop it more. We want to know more details. That's when this group in Bristol, Bridge Group, we started to do. About 10 years ago, the nuclear waste services started to fund a PhD in our group, Dr Xin Ren. Some of you might know her. Yeah, she started to do this as her PhD project. And this project was further developed through the funding by not only the NWS in UK, but also SKB in Sweden and Posiva in Finland. We've also applied it with the KAERI in South Korea by Charlie. And then last year, the nuclear waste service come back to us and want us to push it forward and do more for the UK. That's where I've started to be involved. And some of my results going to talk to you today. Yeah, so our solution is not that general circulation model is undoable. Then instead of using the EMIC model, we decided to use an emulator. You might ask me what's the difference between model and emulator. It sounds very similar, right? Model is like built on lots of physical process, so lots of equation being involved and although some parameterization involved. You give it the input, it will give you prediction. And the emulator is usually it's not built on physics. Probably will be some physics involved, but not so heavy. And it will just mimic what the model's doing. So the emulator will mimic what HACM3 do. You give it the same input, and we expect it will give us the same output. This is what we expect. Compared to the model, it will be very efficient. This is a very big advantage, and high resolution as a model, and also accurate as a model. This is what we want. Okay, here goes the main result of my work. First of all, I'm going to show you the whole workflow because there are not only emulator being involved, but many other procedures and models being involved. So I'm going to tell you step by step. Hope you will keep awake. The the first information we want is to decide the emission scenarios we want to choose for the future, as I mentioned before, and also the opposite data for the future. These are the two main drivers for the climate in the future. After we got these two information, we tell the carbon dioxide model that it predict the carbon dioxide concentration, atmospheric concentration in the future, and then use a conceptual sea level model. It will take the opposite data and carbon dioxide data, predict how's the global sea level, which means the land ice volume will change in the future. And then we give this information to our emulator, but before that we need to train it well. And then it will give us prediction. This is what we want. However, this is not all we want. We want a more detailed prediction. So we apply another downscaling procedure. It will downscale the prediction we got and give us more details on the specific site of GDF, how the climate will be in the future. So here's the whole workflow of my work. You might feel like a little bit messy because there are 4 models involved, 4 input data initially we need to have, and some intermediate data in the middle procedure, and there's loads of outputs. But I won't tell you all the things. I will just show you the main things step by step. Okay, so let's start it from the easiest one, the orbital data. The orbital data, we calculate it from equations of celestial mechanism, as I mentioned before, and it comes from the solution of Laska. Here's the example I showed you before. We are here at this moment, and in the following Ka, 1,000 years, the summer insolation we accept at 65 degrees north will decrease soon, but soon after it will come back. And you can tell there will be circles, not only one, but thousands of circles in the future. So that's the orbit change in the next 1 million year. Now we got the orbit data, 1/3 is done. Then the second one, we decide emission scenarios. So as I mentioned before, we want to take the most high impact scenarios defined by IPCC. We take the SSP scenarios, low emission scenario, high emission scenario. But we don't only want that, we want more. So I added 2 more scenarios in this project. One is natural scenario. We assume if there's no anthropogenic carbon emission, what will it be in the future if there's no human? And then another scenario is the most extreme scenario. It's called 10,000 petagram emission scenario. It's even higher than the highest SSP here. We assume we will impose 10,000 petagram carbon into the atmosphere. What will it be like? And then we give it to the impulse response function carbon dioxide model. It's been calibrated with the carbon cycle model CGMI, and it considers the fast response, like the oceanic mixed layer carbon dioxide uptake, and also the slow procedure, including silica weathering and the deep ocean equilibration. So it takes all the response from all the time scales and give us a prediction of what is the carbon dioxide, what is the atmospheric carbon dioxide in the next 1 million year with this emission. So here's the result. You can say, no wonder in the highest 10,000 petagram emission scenario, we will reach to like 3,000 ppmv in the next 1 Ka. Like the pre-industrial level is 280, but next 1 Ka it will be 3,000. And there's something wrong on the natural scenario. It should stay there. But yeah, and the higher emission scenario will have like high carbon dioxide to over 1,000 ppmv and to acceptable ppmv. And for the lower scenario, it will drop down. And after the first 1,000 years, it will gradually drop down by the weathering and other process. So here's our first result: the carbon dioxide in the future if we impose the carbon. We got the orbital data, we got the carbon dioxide concentration. The next step we need to fit into the emulator is the global sea level. So here we use a conceptual global sea level model. It's been built based on the past records and built as a function of orbital and the carbon dioxide. So we need to tell them the orbit and carbon dioxide. And here's the result. As I said, it's a parameterization of the procedure. So there are lots of parameters being involved. We want to be so confident that this is for sure. So we sampled 19 ensemble members of those combination of parameters. It will give us the possibility outputs from the sea level model, like to sample the uncertainty. Here's the result. Follow the changes of carbon dioxide, global sea level will also increase by 25 meters in the future if we take high emission scenario, which means here we stand now will become submerged in the next 1 ka, but gradually it will drops down, and this dash line is the place we are going to build the geological disposal facility. Now it's like around 25 meters under the sea level. But if we don't emit any carbon dioxide, or if we follow the least emission scenario, it will become up to the air in the next 60 thousands of years. But if we take the highest scenario, they will stay oceanic till the next 500 thousands of years. But no matter which scenario you take at this moment, they will all converge after around 550-ish thousands of years. They will then be dominated by the glacial interglacial cycles. But however, it will take 500,000 of years, and before 500,000 of years, it's still very, very highly relevant to the carbon we emit. Okay. And also we can't just use the carbon dioxide we got, because we have a hypothesis that we stay in interglacial, but also carbon dioxide will highly impacted by the glacial period. I think it's okay, right? In glacial period. So I also take the equation built by Natalie. She studied the relationship between global temperature and carbon dioxide, and we use that equation to update our carbon dioxide concentration level, and especially update those on the glacial period. So here is an updated carbon dioxide curve. It's the same, like after 600-ish, they will all converge. They will all dominated by the glacial interglacial cycles. But before that, there will be big difference between them. So this is our second result. We got the carbon dioxide concentration, global sea level change, and now it's time to fit our emulator. No, we need to build it first. So before we build that, as I said, it's mimic what HCM3 is doing. So we need to build the training data to train the emulator to learn machine learning techniques to learn the behavior of HCM3. So here, the philosophy to build the training data is that we want to include every possibility, the highest one, the coolest one, and then do interpolation rather than extrapolation. So the three drivers we need to give to the emulator includes global sea level, orbits, and carbon dioxide. We give it the possible range in the future. Here's the range in the future, and then use the Latin hypercube sampling and also the previous LGM, last glacial maximum simulations as training data. Here's a cube shows every simulation we've done. One dot here means one simulation. The position of the dot in the cube means it will tell you the three parameters you get. And for the high glacial scenario, we take the last glacial maximum simulation from Sangria, And for the high global sea level scenario, we use Latin hypercube sampling to sample the space in all the parameters. So in total, we fed 162 simulations into the emulator. And the emulator will learn from this 162 runs. This is the structure of my emulator, which I spend half of my time on, is to first of all get all the training data, because it means like over 100 maps. We need to decrease the size of it. So I use the encoder. Here I take principal component to decrease the dimension size of it, and then use a regressor to learn the relationship between the forcings and the response. So here's the main body of my emulator. And the training data is ready, the structure is ready, then the emulator is ready. So here shows the prediction procedure. I gave it the information, and after decoder, it will give us predictions. Oh, if you want to check out how we validate the emulator, including the application of the emulator to quaternary climate, including the comparison of its outputs with the records, you can check out the Chinese latest paper. Okay, we got everything. Then boom, we got the variables. Before I show you all the variables, I will tell you the downscaling part. I might scale it because we don't have that much time. Okay. Yeah, here's an animation built by SAP. If you want to check out it by yourself, you can visit this website and play around with yourself. And other than temperature, we also have precipitation, wind, and vegetation, and everything you might be interested in. Some of you might have ever seen this animation before. It's very cool. Yeah. So this shows the 3D variation of how climate change in the future, and the results come out of our emulator. It's very fascinating, but our topic is focused on UK. So I need to stop this animation, show you some maybe boring analysis on UK. I will go back to the animation later. Here is where we are going to build the next, if I understand correctly, the next GDF facility is near Copenhagen over there. And I give you one example. One question we concern the most about is how likely is it we'll have an ice age over that place? So we want to answer this question first. And in order to get more confidence, we have like three methods to solve this problem together. One is to emulate ice sheet. We can emulate everything, right? Then we emulate ice sheet directly. To cross-validate, we check the relationship between temperature and ice sheet, and we infer the likelihood from the temperature change. And also we infer the likelihood from the global sea level change and the ice sheet. Because global sea level, it means like the land ice volume, but we don't know where. So we learn from the relationships. These three approaches can cross-validate each other and tell us the answer. So here comes the first one. I emulate the ice sheet directly. I divide the region into 4 regions. First is as what it is now is under the sea without ice sheet, and the second one is as what we are now in Bristol. We are in area but without ice sheet. Another one is under the sea, but there's sea ice sheet cover on top of it. And the last one is aerial but covered by ice sheet. So let's say what this site will be in the next 1 million years. Here's the result from the top to the bottom is from the natural scenario, low emission scenario, to the highest extreme scenario. I'll tell what does it mean. From the natural and low emission scenario, that means in the next 80,000 of years, that site will likely be aerial and covered by ice sheet. And in the intermediate, emission scenario, it will be postponed to nearly 130 Ka, and even later on the high emission scenario, and also the likelihood is decreased to around 50 or less than 50 under SSD 5A5. And under extreme carbon dioxide scenario, the onset of that site to be aerial will be postponed, will be significantly postponed till 550,000 of years. So this is a story we can tell from the result. And also the fraction of that site stay below sea level and will be significantly increased as the emission increase. So this is the first story we got from the emulate of ice sheet. Then what's the other two approach will tell us? Are they correlated with? Are they the same? And okay, so here's the relationship between the temperature and ice sheet. This is a plot shows a relationship between the surface air temperature anomaly versus the ice sheet present at this site. If we cross a certain threshold, there will be no training data shows there will be an ice sheet. If we below a certain cold threshold, we will simulate ice sheet present at this site. But temperatures in between, there is a maybe. So here is the region from combining the threshold with the temperature prediction. It's very similar to the previous one. We are happy about that. Like on the low emission scenario, like the region will stay warm from the first 100 Ks. And on the intermediate scenarios, it will stay longer. And in higher scenario, it will stay even longer, then force into the intermediate and the cold region, which will create ice sheet. And in the extreme scenario, it will even stay even longer to nearly like 600 Ka. They will be half of the member forced into the intermediate, not even the cold members. And the fraction from the lowest one to the highest one, it will the fraction of the cold region and the cold region and the intermediate region will decrease, and the red pie will significantly increase. This is the same as the first story we are happy and confirm our conclusion. And how's the last approach? The global sea level and ice sheet creation. This is a similar figure, because like the ice sheet present on UK is not always follows a land ice sheet variations on the Earth, because sometimes they will build ice on somewhere else, like North America or Europe, but not over UK. So we can still get some information from that. Similar to the previous one, across a certain threshold, when the global sea level increases to some level, there won't be ice sheet. And when the global sea level drops down to a threshold, which means there are a lot of ice sheet built on the Earth, there will be also ice sheet over UK. And in the intermediate region, there will be maybe. So from the sea level, combining the sea level and this threshold, here's the result. Very similar. From the lowest scenarios, the globe will stay, the site will stay in warm region till 80, 60 thousands of years. In the intermediate, it will be like 150. And in the higher one, it will stay longer. And also the ratio of the intermediate region will decrease a bit, but not much. And in the highest scenario, we are kind of confident that the site will stay in the warm region till 550 K from now. Yeah, and also the ratio increase like increased by the increase of carbon emission. Yeah, cross-validate with this three methods, we all get the same conclusion, and now we can confidently say, under low scenario, especially nature scenario, the ice sheet onset will be around 60,000 of years from now, and the fraction that continent site spent under the water will be about a quarter under this scenario, and those numbers will increase as the emission increase. Under the highest scenario, it will significantly postpone the onset of ice sheet, and delaying the ice sheet present to around 550 or 600,000 of years is a lot. And also the fraction that this site stay underwater will be significantly increased from a quarter to nearly 3/4. So the design of the GDF will change significantly on the different scenario. So now it's a big challenge to them now. Yeah, you might say this is a very complex workflow. Four models involved and many hypotheses involved. So we definitely have lots of limitations. The first limitation comes from the training data, because when we can't assure that HSM3 is definitely correct, there is uncertainty from the boundary condition. We might give you the wrong boundary condition, where the model itself, the structure of it might be wrong. So this is the first uncertainty we need to consider, but very difficult to solve. And the second limitation is the limitation from carbon dioxide, because we need to run the carbon dioxide model to get the concentration. There might be uncertainty over there or over the updating procedure. And sea level forcings as well. The conceptual global sea level model is a parameterization model, and we already sampled 90 members, but there are still large uncertainty exists there. And the third limitation is the approach in the emulator. I built it, so I know more about that. The emulator is just an approximation of the HSM3 by itself. It can't do exactly what HSM3 is doing. During the procedure, like the encoder, PCA, and the regressor, what is called? Gaussian process regressor, they will have, and I've also tried two different proper machine learning approach. They will introduce me some uncertainties. So these are the uncertainty from the emulator itself. And also we will have the uncertainty from the downscaling approach, although I didn't show you much detail, but there are uncertainty existed there. Yeah, so what are we going to do? Now I've already finished this project, but there are many things we can do in the future. The first thing we can do is to address those existing limitations, addressing them one by one. And another thing we can do is to do the ice sheet modeling, because as I said, although the land ice sheet, they might increase, but we don't know where will it increase, where will it build on. It might build on North America, or it might build on UK. We don't know. So we need to find the better approaches to run the ice sheet model to solve that problem. Yeah, so this is my talk, and we've done this work for many other agencies, and this is our previous reports. I didn't show my here, but yeah. And if you want to read them, here's the linkage to those reports. And here are all the reference being used in this report, in this talk, and here's the animation. I bring it back.
Very much. Thank you for enlightening and slightly worrying talk. That was fantastic. We've got time for some questions. If anyone online has any questions, please put them on the chat, and my colleague Meg will have a look at them. So in the room, we got any questions for Jim?
Yeah. Yes.
Do you have any video for the regional variability over the UK? Obviously, in the map you showed that the UK is about 5 wind buses of the model, which you then downscale to the particular area in the north.
Yeah.
Would you get similar results if you look, say, in the south again, different greenhouse?
Yeah.
The reason I ask is that the work I did for SKD, which is not really about today, gave pretty similar results. So is it a large scale thing we have seen?
Yeah.
Or if you were to look, say, Southern England, would you see something different?
This is a very good question. I only checked one side because we downscale it to like 1/2 degree, and we care about Copenhagen. So I checked the temperature and the precipitation change over the Copenhagen side, and luckily it has the same story as the larger downscale story. But I didn't check other story because it's been like the information we feed into the downscaling is the predicted weather from the larger box. So I assume it won't. I just assume I can't confirm. I assume they won't reverse the story. Yeah, and at that side it is, but other side I'm not so sure. Yeah. Hi.
Is there a best case scenario? And is the best case scenario for GDF the same as the best case scenario for human beings?
Best scenario for human beings. You need to define what is best mean, because like if you want to keep consistent as what we are now, probably we can find some intermediate or like low emission scenario. If you want warmer weather, probably the higher emission scenario is the best. If you like to stay under the water, higher is the best. But if you want to back to the period like the whole Earth is dominated by the natural process rather than anthropogenic process, the natural scenario is the best.
Yeah.
Yeah.
We do actually have questions in your minds. Hopefully this answers. If you're able to speak online, please do, or feel free to put it in the chat. You just let them know.
Peter Watson, we believe you've got a question online. Can you unmute
Yeah,
yourself?
thanks,
great.
Ian, for that. It's very interesting. I was just wondering, you know, given it looked like the kind of model resolution you had is quite coarse compared to like the points where you're trying to predict information for. So I just wondered, I'm sorry, by the way, I missed the first few minutes of your talk, so maybe you addressed this at the start, but can you say anything about the sort of, you know, model quality here and how kind of, you know, it's fits for purpose for looking at this? You know, is there anything you can kind of say to kind of you know, explain that, you know, the model should be trusted for projecting kind of hundreds of thousands of years into the future? For example, have you tested it on like historical ice ages and seen a good correspondence there or anything?
Yeah, this is a very good question. Like when we build the training data for the emulator, as I mentioned, we want to include every possibility, and we take the last glacial maximum to train our model. So this is like long enough from the past, and also we want to consider like when we build the training data, we consider the highest carbon dioxide concentration. So it's rather than extrapolation, it's more like interpolation. And also from Chinese work, we compared it with the previous records, and it fits well. So we can confidently say we tried our best. Yeah.
I mean, do you not have like a held out test period, like ice ages that the you know, the model's not been trained on to see does it still, you know, is the of the observations within the range, within the uncertainty range of the model's predictions or anything?
The way I validate the model, I just from the statistical way to validate the model, because we have enough training data, not enough. We have over 100 training data, so I use two ways to validate it. The first one is 10% out, 10% take 10% out as validation as test data set, and the rest of them to train. And another method I use is called leave one out. Every time I leave one simulation out of the training data, use the rest to train, and then compare the prediction with the one I left, and then run it for 162 times to say if the truth dataset and the prediction dataset, if they match. This is the statistical way I validate my emulator.
I was kind of getting out testing against observational data, but I don't know, maybe it's best to move on.
Yeah, for the observational data, you can check Chinese paper. We compare it with the data from the past on some site using the emulator. Yeah. Yeah.
Hey, yeah, really enjoyed it. Cool. And maybe not a question for you, but I was wondering what the impact of this research is. Like, say, if we said with some like 100% certainty there was going to be an ice age over this site, would that impact the planning of this facility, or would it more lead to just like a warning system?
You mean what does it mean to us?
Yeah, would this actually change where the facility was going to be built?
Yeah, this work is built in the background to assure the safety of the facility. For us, I think we could also infer something like to us, like when we build our house, or when we build some build a city, or like human immigration. We can also take that climatic information. Yeah.
So like when the planning this facility actually considered like, is it a key requisite of their planning policy? They consider the climate really interesting, or is this kind of like the planning been done, this facility's going ahead, and they want to know what cautions to take?
I don't get. Could you please simplify your question?
Basically, like, is this facility happening?
Yeah.
Yeah. So, what difference will it make to how this facility, if like the results of this research, what difference will it actually make? So,
this is something engineer should answer. Yeah.
Perhaps I can offer a bit of perspective. So I think you're right in asking the question. At the moment, we don't have a site specifically for the geological disposal facility in the UK. That's still an ongoing process. When we look at nuclear facilities more generally and about basically improving safety cases, they'll look at climate predictions within their operating lifetime. So for a nuclear reactor, they'll look at the sort of extreme weather that they are likely to encounter over the next 100 years. And that will be the same in the geological disposal facility. So they'll have a kind of envelope for the work that they're operating within, and then the designs to influence how they're going to operate the GDF will be influenced by, if there's going to be an ice age. So that can be things, for example, with like the containment of the nuclear fuel. They might put as an example, the Canadian design is using a copper sort of pill-shaped system to contain nuclear fuel. If they're guaranteed ice ages, they might have a thicker copper shield on the nuclear fuel. Things like backfill in the bolts that they're engineering, how are they going to integrate that, and what does that need to be to combat things like ice ages? So it is influencing the design. Not necessarily in the placement, because there's different things according to that, but it's all about how you can achieve that safety case to deliver safety over that period of time. Sorry.
Thank you for helping. Yeah.
I was wondering if there were any conclusions that you seem to be coming to with all of the simulations, like regardless of what's kind of best case, worst case changes.
Yeah, I think the thing they care about is how many percentage will the facility is going to be underwater or experience the glaciation, and when will the glaciation happens. So this shows on my previous slides, and also like how the precipitation, wind will change in the future. Yeah, and one of our major, there's no very big changes in the influence on the wind, but precipitation. If we are on the high emission scenario, we will have like much larger precipitation in the first if I remember correctly, in the first 200 years. But if we follow the natural scenario, it will be dominated by the orbital variation. Yeah, this is the conclusion other than the conclusion I gave there. Yeah. For example, the ratio, like a quarter of the time, that side will stay under the water, will increase to 3/4. I think this is something they consider a lot when they build the vault. Yeah.
Maybe I can ask a question.
Sure.
If anyone is speaking. You talked a lot about glaciers and sea level. What about extreme heat? Because that feels quite a very relevant topic, especially in the last month where we've had really high temperatures in the UK. What kind of heat levels are you looking at and temperatures in your models?
It's contains in the first temperature region figures I gave. Like, I don't remember. I think it will be like, if I remember correctly, it will be 90 degrees Celsius warmer under the highest.
Zero.
If I remember, not 90.
Oh, 19.
19. Sorry, and it will be ridiculous. 19.
Okay.
Sorry about my.
That's still fine.
19 or 15. Yeah. If it's nature, then we'll goes up. But if it's the highest one, will be 19 or 15. Yeah.
So we could be looking at temperatures over 50 degrees C in the UK.
Yeah.
In
next
too...
one.
Wow.
But there'll be loads of carbon emit to 10,000 petagram. But I hope it won't be like that. Otherwise, we'll be real. Yeah.
Really like the project. So main finding is this 25% versus nearly 3/4 period of water. And maybe this question is more for engineers, but if you're designing a facility to be underwater for 250,000 years, surely like the waterproofing of the facility is the same for 250,000 to 750,000. I don't know, maybe this is just because it seems like a long time, even 25% of a million years is a very long time.
I also want to know the answer. I assume it will be very different. Like, just imagine over half of the time is under the water, or less than half of the time under the water. You might treat them differently, because like if you are on the ice margin or on the water, hydrology procedure will affect it the most. But if it's inland, other things like the vegetation or the precipitation might be the most highly relevant of it. I'm not so sure. This is my guess. Yeah.
Any final questions? Okay, let's thank Jin again.
Thank you for listening.
Thank you very much. I think we've got a little slide. Okay, so thank you for coming today. In case you aren't aware, the University of Bristol, we're recruiting deputy directors for the Southwest Nuclear Hub. So if you want to get more involved in the work that we do, come and speak to myself or Meg, or there's a QR code that takes you to the job advert. It'd be great to have those of interest in that. We have the next seminar. Well, we're having a pause in the seminar series over the summer, and we're going to start up again in the next academic year in 2026/7. So our next talk will also be on geological disposal facility from Professor Claire Porkhill, who's one of our directors. That will be on the state of play of the GDF in the UK. So dates to be decided, but that will probably be in September. So maybe see some of you there as well. So let's thank Jin again, and thank you all for coming.